Good morning, everyone. Today's webinar, When Loops Collide, will begin shortly at 10 o'clock. Thank you. Good morning, everyone, and welcome to our webinar, When Loops Collide, Overcoming the Challenges of Interacting PID Controllers. All of your microphones are muted for the duration of this webinar. Please submit any questions that you might have using the question submission utility here on the GoToWebinar platform. Today, we're very fortunate to have presenters from both Control Station and Aquarius Software. Chris Christie is Director of Services here at Control Station, where he is responsible for the development of value-added process optimization services and for leading a team of expert engineers in the delivery of those same services. Prior to joining Control Station, Dr. Christie was Process Control Capability Lead at Cargill, where he successfully supervised an enterprise-wide control loop performance monitoring program involving over 100 production facilities. Nelson Silveira Neto joins us from Aquarius Software, where he is a sales analyst in the company's business development organization. Nelson's focus is on leveraging technology-based solutions to address the process diagnostic and optimization needs of manufacturers located throughout Brazil, particularly those in the oil and gas and food and beverage industries. Nelson earned his undergraduate degree in electrical engineering from USP Polytechnic University, located in Sao Paulo, Brazil. Control Station has been advancing the science and practice of process control since 1988, earning numerous awards for excellence and innovation across more than 3 decades of continuous development. Headquartered in the United States with offices in Ireland, Control Station serves a global client base with the help of its solution partners, bringing localized expertise and support to a global clientele of process manufacturers. Perhaps most telling is the company's reach within the world's largest manufacturing organizations. We're proud to support over half of the manufacturers listed in the Fortune 500. Aquarius Software has established itself as Brazil's leading reference for industrial automation technology, delivering a curated portfolio of globally leading software solutions through a network of specialized integration and channel partners. The company is particularly distinguished by its commitment to after-sales service and support, an area where Aquarius has earned consistently high marks and one that reflects a relationship-driven approach to long-term customer success. We're pleased to have them as a value-added partner in bringing today's session to process control professionals across the region.
All right, thanks, Dennis. So for today's webinar, we're gonna go through a few sections here. So initially, we'll talk about loop interactions and their economic impact. So, why single loop thinking, what are the pitfalls of that? We'll introduce loop interactions and talk a little bit about why they occur, and just give you a brief idea of what the economic impact is to manufacturers and how you can convert that hidden cost into a competitive advantage. Then we'll go a little deeper and look at how we diagnose interactions, talk about the tools that we use and what sort of metrics are involved in isolating and quantifying loop interactions, and how we can misdiagnose, if we don't have the right tools, how we can misdiagnose other forms of control performance issues with we can misdiagnose interaction or other forms of control issues. And then the next step, we'll look at, once we've diagnosed interaction, how do we go about tuning and how we go about configuring our loops to reduce the impact of interaction in our processes? And finally, we'll look at a case study in the mining industry of how we've identified interaction and been able to resolve that for copper mining. So next slide, Dennis.
Hey guys, I'm very excited to be here as well. Now we're going to head to our first survey question. Throughout the webinar, we'll have a few questions, a few surveys that we encourage everybody here to answer. The idea is we want to better understand how you face plant interaction issues, loop interaction issues, how, these challenges surface to you, what is your experience with them? So here for the first question, we have what is the greatest economic challenge your plant faces due to loop interaction? And below we have a couple of options that really showcase, some ways that loop interaction can interfere with your operation. So variation in product quality and associated waste. We have high energy consumption. Another one is excessive operator interventions and safety issues. And also accelerated wear and tear on production assets. And last but not least, some of you may not quantify economic impact, and giving that honest answer really is a great way to kind of start this conversation and understand where we can follow through. Chris, what do you think about these options?
Yeah, these are all issues that I've faced in, throughout my career. And I think often, at least for me, like until we had loop performance monitoring tool, we very rarely were able to identify, interacting loops just easily. Yes, just by virtue of knowing how certain equipment or units behave, we could understand the interactions, but oftentimes that was a hidden issue in our process, and therefore even being able to determine the economic impact of that was quite difficult.
No, definitely, and I think really having a tool or a software that can help you analyze everything holistically so you can get the bigger picture is definitely necessary to give a clear view of the issues you're facing. But what I kind of like about the survey is to kind of get a gist of what people usually look before having a tool, or even if they do have, what is their main concern, what pops out the most. Because as far as I know, and you know even better than me, all of these, the first four options are usual challenges or usual problems that arise due to loop interaction, right?
Oh yeah, absolutely. And again, it depends on the equipment that you have. Some, we have here high energy consumption. Well, that's for units that use a lot of energy, but then there are throughput related issues, so that you end up with quality and waste issues there as well. And mechanical issues are also a big part of just interaction issues, the oscillations that come with the wear and tear of valves and final control elements. So indeed, I see here we've the survey is ended, so we can go ahead and show the results.
Yeah, okay, I think we're seeing them already. I think it's interesting. We got the highest vote is for not quantifying economic impact, and as I mentioned before, it's important, right, Chris, to kind of be honest in this first step, so we can explore what we can do to start measuring this and start facing this issue, right?
Yeah, and I think it makes sense because they're the highest score here is that it's not quantified, and that's because it's hard to identify the interaction. And so again, just by virtue of coming to this webinar, you all will see how you will understand the workflow of how we go through diagnosing interaction across our loops and across our units. And so this is a good way to segue into our next, first slide, is to talk about why single loop thinking, how that falls short. So, just throughout our process control training, we tend to focus on, individual loops, single loops, tuning of those. But in reality, we have many pieces of equipment that are working together. And so in industrial processes, we often have multiple loops interacting. And so, interaction is basically, you change the you change a loop, and so the output of one loop is going to impact the process variables on adjacent loops. And oftentimes, we as engineers, we often focus on, we're taught, and therefore we're taught to focus on individual loops. But in reality, we want to be looking at multiple loops together. Our processes are interconnected, and therefore, just thinking about a single loop, it provides a blind spot for us.
Yeah, definitely. And I think it's a bit of a shame that we focus too much on single loop tuning, because if we have, for instance, a process that is very affected by loop interaction, that ends up just being kind of a wasted exercise in retuning, because it actually doesn't fix the underlying cause. So just, it's important to keep this in mind, that real processes are interconnected. And if we don't look at it that way, we end up just not actually fixing it.
A wasted efforts, indeed.
It's a wasted effort, exactly. Next slide, please. Yeah, and to continue on what Chris already introduced, we're going to talk a bit about what loop interaction actually is and why it occurs. Chris already mentioned correctly that the phenomena itself is observed when the output of one controller influences the process variable of another loop. And the underlying issue that causes loop interaction is physical in nature. So you can think about shared process streams, common utilities, thermally coupled vessels. For example, if you have a series of loops that share a common steam header, if one of the consumers, if a specific loop starts to draw a little bit more steam, the pressure in the entire line drops, so it ends up sagging, and that affects all of the other loops that share that same common utility, which in this example is a steam header. And to know this is to understand that interaction is inherent to process design itself, and therefore it cannot always be eliminated through control strategy. And to also kind of quantify and measure loop interaction, it's important to understand the relative gain, speed, and directionality of the loops involved in this interaction. So definitely kind of mixing together the understanding of the physical source of your process and also the degree, the severity, the intensity of this interaction is your first step towards actually managing it.
Yeah, and one thing I'd want to call out here, Nelson, is that this is interactions are purely inherent in, even you cannot resolve this in the design part of you're designing your process or your plant. This is purely part of the operational aspect of manufacturing. So you'd only see this once you have commissioned your process and the plant is running. If the plant is not running and it's just purely on paper, you're not going to realize this. So this is definitely an operational issue.
Most certainly.
Next slide, Dennis. And to the point of it being an operational issue, the instability that comes from interaction causes quite a number of, has an economic impact. You have issues with quality. You end up using more energy than you need to or have to, and you end up with a lot of yield losses. There are also mechanical issues that are associated with just by virtue of the oscillations that happen. Your valves and final control elements are doing a lot more opening and closing, speeding up or slowing down, and so that causes wear and tear on your issues or on your equipment. And so to the point of, this is not just on paper, like these cases are not just theoretical, you can actually quantify them. And so through just process control research, we've seen that manufacturers lose about 1 to 3% of revenue and productivity costs, they lose a 1 to 3% of revenue or cost just by virtue of poor PID control. So a facility that's $500 million a year is losing about $5 to $15 million per year of poor PID control, which interaction is a part of. Loop interaction is a part of that. So there's a huge cost to manufacturers.
Yeah, and I think it's kind of an unusual opportunity, because for me this cost kind of feels or maybe feels to some customers like a sort of loop interaction tax that you have to pay simply because your loops are interacting, but that's not really the case. It's definitely due to poor PID control, and so it's kind of just value that's left at the table. It's really a cost that you don't have to pay, but you end up paying. So I think it's a big opportunity for customers to start leveraging loop management solutions to address this issue and they have stand so much to gain. So I think it's really puts into perspective what amounts, what values we're talking about. Next slide, please. And to follow up on that, we also have kind of the other aspect of it. Okay, we're fixing a loop interaction, we're addressing this issue, and we're stripping the hidden cost. What do we gain after we do that? So what is the competitive advantage by addressing this afterwards? The thing is that facilities that do manage loop interactions systematically, throughout the whole process itself, they can reduce their variability, which allows them to operate closer to their process constraints with tons of confidence. And just by doing so, they are enabled to reach tighter product specs, higher yields, to improve their energy efficiency. So it's great throughout all these measurable, impactful scenarios. But not only that, there's also the other part we mentioned at the beginning, where Chris put it. Operators, engineers waste their effort trying to retune loops that are interacting, and we just saw that isn't the really nice or correct solution. So just by managing these loops systematically, operators will spend less time intervening and more time monitoring and optimizing, so they can spend more time on doing other stuff that is perhaps more impactful. So definitely we have two distinct and very important impacts of stable, well-tuned interacting loops, which is the financial side that compounds definitely through energy, quality, throughput, equipment maintenance as well. And also engineers and operators will be spending less time on trying to fix something that wasn't working before. What's your take on that, Chris?
Yeah, this it improves efficiencies both from the production standpoint. Now you can operate closer to your the limits of the process, but it also, as you say, reduces make your operator your ops teams more efficient. And so by virtue of having loop monitoring tools that you can identify all the issues, interactions being one of them, it allows your ops team to be a little bit more efficient in identifying the real root cause of the issue and resolving it, rather than chasing the troubleshooting and chasing down things that or misdiagnosing problems that we have. So yeah, next slide, Dennis. Yeah, so here I'd like to just segue into next month's webinar, where so we see here it's talking about converting blind spots to from blind spots to insight, and this here we're talking about how we can use data-driven analysis to do plant-wide controller performance audits. And so this webinar will introduce a methodology for conducting, your comprehensive PID performance assessments to uncover problems associated, problems that undermine plant performance. See, problems like loop interactions. So how do you do that on a plant-wide basis through loop performance audits. Maxime Lachance from another of our partners at BBA will be talking through this. So stay tuned for next month's webinar. And next, Dennis.
Great. And that's a great point to start our next segment, which is diagnosing loop interaction. And here in this slide, we're going to present a couple of signatures, kind of the fingerprints that loop interaction leaves behind, and how we can use them to definitely diagnose loop interaction. The first one you can see here, represented by this wave symbol, is oscillation. And it's very prevalent in interaction-driven problems. Whenever oscillation appears across several loops simultaneously. Following on that, we have loops also that outperform in manual mode than when they are in automatic. So whenever you notice that you set your loops in automatic and they tend to oscillate a lot, and you switch them to manual and it looks like it's better, they perform better, that's a classic interaction indicator. And following on that, the signature that's represented by the Band-Aid symbol, which is I think really paints the picture on this one, which is loops that briefly improve after tuning, but then they resume the same oscillatory behavior, they degrade again. That really suggests loop interaction, really suggests neighboring loop influence. And the last signature we have here, which is represented by the boxing glove, it's definitely illustrates the issue where operators are complaining about loops. They mention or they comment that loops are fighting each other or they require constant intervention. It's one of the clearest signals for diagnosing loop interaction. And all of these and even more can be seen and can be really put into perspective when you run trend analysis across multitude of loops simultaneously. And it's often the fastest way to confirm that loop interaction is really present. And what do you think, Chris? Do you think any of these fingerprints any of them are more reliable than the others? What's your take on that?
I've seen all of them, and have been had to diagnose interacting loops, or without a loop performance monitoring tool, it's really hard. You have to just look at it's often spend time just looking at multiple trends of data, superimposed on each other, and it gets really difficult. And so if you move to the next slide, Dennis, one of the easy ways that we're able to identify interacting loops is by the power spectrum analysis. And what that does is we're taking each loop and we're identifying the major frequencies of oscillation that is happening for in each of those loops. And within Plant ESP, we're able to not only just identify the power spectrum for individual loops, but we're then able to sort based on that, the dominant frequency that we are seeing. And we can sort multiple loops. Well, first we can group multiple loops and identify the frequencies for each of them, and then sort based on the main frequency that we're seeing for one, and see how many other loops share that frequency. Because when two or more loops share a similar dominant frequency, that's how we know that those loops are oscillating together. And then from that, we can use another metric that we'll talk about later, cross correlation, to see which of those loops are leading or lagging that, to really pinpoint where to start focusing on resolving the tuning issues. So this, by using power spectrum, we're able to identify the dominant frequencies, and we're able to identify where, what is a interaction-based oscillation versus noise or stiction or any of the other types of problems that can produce oscillation in loops. So point here is that shared oscillating frequencies across loops we'll be able to confirm interaction there, and then that will allow us down the workflow of resolving these interactions.
Yeah, fantastic. And I totally agree, and it's kind of a surefire method to eliminate any doubt. As you mentioned, You can really distinguish interaction, oscillation from disturbance. You know, stiction, you mentioned noise-driven variability. So it's definitely a great tool to have. Next slide, please. And Chris, we have already started to really paint this picture on how we can scale this diagnostics, on how we can use, as you mentioned, spectral analysis, how we can use other tools to really scale this diagnosis into a whole plant, to hundreds of loops, to really be able to see everything, to put everything into perspective. And as you have mentioned, and as we have talked throughout, the main way to do this is to really adopt a CLPM solution, a control loop performance monitoring solution, which can leverage historian data to provide a continuous multi-loop record of PID controller behavior. And running these tools that you mentioned, power spectrum analysis, cross correlation, across these these historian tags, can identify loops that are coupled, that face interaction at scale. And this is kind of a good news. It's kind of good news for our customers, because most of them already have historian. They already are organizations with a local or a enterprise historian, and a solution can simply connect to that and provide all of this diagnostic data, can provide you all of these insights into not only loop interaction issues, but other issues that arise from control loops as well. So we have been kind of building this up to kind of reach this point that the CLPM solution really is kind of the way to go. Wouldn't you say so?
Oh yeah, and back as a when I was doing analyses on plants, all we had was data in Excel and just looking at Pi screen, just trending different tags on Pi. And so one of the disadvantages of doing that is that you can only select loops or variables that you are aware of, and at some point in time it becomes too much data for you to humanly process, and you end up missing some of those loops that maybe interacting with each other, or maybe you get lucky and find them. But having a tool like this takes out all of that messy work for you and does all of those analyses, and just provide metrics or nice graphs for you to look at that really zones in on the issue. And so if you go to the next slide here, Dennis, we'll call out one of the common or some of the common misdiagnoses we end up having. So again, without a tool like this, we end up identifying what are truly interaction-driven oscillations. We can sometimes misdiagnose those as, valve stiction issues or noise sensor issues, or even process-related issues. And by misdiagnosing those, or engineers end up retuning loops or resolving stiction issues, or trying to resolve noise or stiction issues, when really it is an interaction driven problem. And so by virtue of having a loop performance monitoring tool that does a power spectrum, that is able to help you sort through those dominant frequencies and identify the loop and loops that are interacting together, we're able to, one, identify the interaction, and then two, it reduces this trial and error method that we used before, and helps us to become more efficient in resolving the issues and root causes associated with this.
Yeah, definitely. And as I said before, if you don't have a tool to help you in this, if you're relying on Excel sheets, or kind of just looking directly in a single loop perspective, if you're trying to eyeball what the issue is, you'll probably misdiagnose it. But if you have a tool such as Plant ESP to help you with it, everything becomes much more clearer. Next slide, please. So now we're heading to our second survey question. As we mentioned before, We encourage everyone that's participating to answer, so we can get, you know, a view about how you look at these issues, how you address them. And right now for this survey, we want to know, how do you currently evaluate loop interaction at your plant? So we have a couple of options here, such as we have no formal interaction assessment process. We rely on operator observations experience. Another is we analyze historical trends from individual loops. Also, we use spectral or frequency domain analysis tools, you know, as we mentioned, cross-correlation, power spectrum analysis. And last but not least, which is kind of the buildup here, is that if we use a control loop performance monitoring solution. So what do you think about this, Chris?
Well, you know, one thing I will say, before I got introduced to these loop performance monitoring tools, my the go-to was always, you know, historical trends, but it always starts from the operators complaining about, hey, this loop or these loops are always fighting each other, and can you help us resolve this, because they're spending too much time, you know, adjusting set points or adjusting things associated with those loops. And yes, that was primarily my the initial impetus to go resolve or actually look further into these issues. But with a loop performance monitoring tool, this made troubleshooting somewhat easier. Not fully easier, but somewhat easier. When operators complain about these loops, you can actually see pull up the features within ESP and actually see which loops are actually interacting, and even be able to confirm that those loops are fighting each other's. And oftentimes you end up finding additional loops that are that are oscillating with those. So this is really that feature. The feature of Plant ESP is a really powerful one.
Yeah, definitely. And I also wanted to mention, as in the first survey, that we had kind of the honest, we don't analyze it question, the option. Here we also have the kind of more honest, we have no formal interaction assessment process. And for anybody that's in that group, I think you're in the perfect place to kind of discuss what your next step should be, what types of solutions you should look to, what types of tools you should be using. So this is definitely the right place to kind of get more insight into that.
Okay, yeah.
Okay, I believe that we are seeing the results now. Is that correct? I think so, right?
Yes. And so here, we see the highest respondents are, the historical trends seems to be the one, because that's oftentimes the only things that we have, and there is no real formal process of assessing it. So it's really based on operator feedback. You go and you look at your loops, your trends, and that's how you determine, okay, yeah, we do have interaction, or I don't know, because we don't have any formal way. So, okay, quite. Next slide, Dennis. And this leads nicely into or tuning in. So now that we have tools to be able to diagnose interaction, the continuous monitoring provides that foundation, because those tools have metrics, key metrics that are just about loop performance in general. So Plant ESP has about 30 plus metrics, all about loop performance, and by having continually collecting that data, and then for loops that are going beyond or outside of those thresholds, those are flagged for further troubleshooting or assessment. And a tool like this provides a good workflow in terms of flagging loops, and then based on which metrics are being exceeded, we can look. It helps direct our attention in it directs our attention, rather than just us going on a wild goose chase. And it helps the workflow. So this provides a more efficient way for our operations team, our operators or process engineers or plant supervisors, to work more effectively in resolving issues associated with manufacturing and production.
Yeah, definitely. And I think you already built up, talked about some key metrics, some things that can help us really pinpoint or direct our attention towards the issue at hand. And I think it turns out to be also a great segue to the next slide. So next slide, please, Dennis, which we are going to talk a bit about some specific KPIs that really expose interaction. And here we have 4 of them that are being presented: oscillation, output travel, percent time to normal, and cross-correlation, which was briefly mentioned before. Well, oscillation, it's pretty clear. We have talked about this a bit today, which is identifying loops that exhibit sustained periodic variability. Output travel as well is pretty direct. If loops are working excessively to try to compensate for disturbances, it turns out pretty clear in this metric as well. And we have talked about also operator interventions, about loops that operate better in manual than in automatic, and percent time to normal is a KPI that really exposes that. When you can uncover loops that transitioned out of automatic control, it usually explains that operators are intervening, and if they're intervening, it's probably due to instability in the process itself. And last but not least, we have cross-correlation, which really is the way to kind of quantify the coupling between loops, to see how their relationship is, how much they are lagging or they are leading across each other. So it's a great metric as well. Wouldn't you say so, Chris?
Oh yeah, I've used these in the past for resolving interaction issues, and I like between the power spectrum and cross correlation, this is a really good way of, the power spectrum helps us identify, okay, what are the loops that have the same or similar oscillating frequencies. And then cross correlation takes that another step further and says, okay, these loops have the same frequency. However, this loop is leading and these loops are lagging. And so it really helps you hone in on what that issue is. And so once you've identified that specific loop that is leading the interaction, now you can go into resolving. And so on the next slide, we talk about how do we literally close the loop, systematically here, and all puns intended here. But one of the things that Plant ESP or Loop Performance Tool has is that it is able to use our non-steady state modeling to extract the process dynamics of your leading loops, or loops in all your loops in general. It is looking at your loops and just continually looking at changes that are made, whether for the output or the set point, and being able to, if it can, it will pull a model out of, for those individual loops. And then it will be able, it calculates a tuning or suggests tuning parameters for you to resolve those loops, so for you to be able to tune them or detune them as needed. So, this is a really good path of, you have a loop monitoring tool that is looking at all your loop performance. You have metrics that look at your, different issues around loop performance, some of them for interaction. And once you've identified that interaction, then it helps you to determine tuning parameters for those individual loops. So it really does close that workflow and make it a lot more easier for you to go from identifying an issue towards resolving that through, in this case, tuning.
Definitely. And also, if you allow me to disturb a bit of the flow, there's something that I just really wanted to highlight on this slide, which I think is really important, which is the kind of the first blue card there, where we talk about NSS modeling, is that it can really extract the process dynamic parameters directly from historian data that was logged before. So we all know how difficult or tough it can be to ask the process team to disturb the process to run a step test to get the parameters so we can model the system. And if you can grab those from a maybe previous step test or from normal closed loop operation that's already logged in your historian, I mean, it's a great thing. We can, the process team is happier with that, right?
That is an absolutely good point. Yeah, it saves so much time in doing step tests. Again, because some step tests, it takes a couple of minutes, but some really do take a couple of hours to do. So by just collecting that information just continually behind the scenes, it reduces the time for tuning substantially.
Yeah, exactly. Next slide, please, Dennis. And now we're going to talk a bit about the strategy itself, which in this case, we're going to present a bit of decoupling and structural reconfiguration. So the first thing to talk about decoupling that we have to keep in mind is loop pairing. And what exactly is loop pairing? It is basically matching each controlled variable to the most appropriate manipulated variable to kind of really determine the severity of interaction. And we do that by running, as we mentioned before, specific tools like spectral and cross-correlation analysis to really identify which of these input-output pairings minimize cross-coupling effects. And by doing that, we can introduce decoupling, which basically just means that we are taking and creating and introducing a compensating signal that can cancel the interaction between these paired loops. And by doing so, by doing this targeted decoupling and reconfiguring loop pairings, we can really produce more sustained improvements than regular tuning, retuning, and this whole process adjustment alone really can. So really, it's a great solution, and it's not really difficult to do as long as you have the right tools and the right mechanisms to do so. Have you had experience with this, Chris?
Oh yeah, and actually the case study that we'll talk about in mining is one of those. But outside of that case study, one of the areas that I've had that experience quite a bit is around distillation columns. Distillation columns are really common with interaction issues, just because we have a lot of heat integration across the unit, and so your inlet stream is heated up by your outlet stream, and the level at the bottom of the column has an impact on the flow. So that is ripe for a lot of interactions there, and so being able to decouple those controllers really does help resolve that issue. But I'd like to just segue a little bit and talk about our next slide, which will introduce I want to talk about our OCE calculator that we have here at Control Station. Or PID or regulatory control in general is one of the ways that keeps our manufacturing plants running. If they are, if our regulatory controllers are not running well, then in general our plant isn't performing well. And so we have at Control Station, we have our plant ESP installed over 200 facilities, and we have tens of thousands of loops that are configured across each of these. And so we are able to do calculate the overall controller effectiveness across the individual plants. But not only that, we are able to help correlate that with some actual values. So we're able, by virtue of putting in a few bits of information of how many loops you have, what percentage of time they're in normal, how saturated are your loops, or how much error are you having. First, we are able to rank the plants across, just by virtue of having all of this information. We can rank, see where provide a curve as to what is common across the industries. And then also you can plug those numbers in just to see, by virtue of where you sit on that OCE curve, you can see what value is there that you're actually losing by virtue of the loops in the whatever state they're in. If some sites are really good, then there isn't much that you're losing on the table. But for most of what we've seen, there is a lot of opportunity being left just by virtue of how loops are operating. So if you go to controlstation.com and go to our tools and calculators, you'll find the OCE calculator in there, and you can plug your numbers in, or you can just use the standard, use the average for across sites, just to get an idea of what value it is there that you may be losing, or that is what opportunity is there for you in terms of improving control at your site. Next slide, Dennis.
Yeah, and now after that brief segue, we're gonna reach our last segment here, which is the case study. We're gonna bring you a bit of insight into a process that happens in the mining industry, which is about froth flotation. And here I'm just gonna provide a brief introduction, and then I'll hand it off to Chris, so you can go more in depth on how it was dealt with, and what were the results of dealing with fluid interaction in this case. So froth flotation is the primary method that is used to concentrate copper from crushed ore before you smelt it or you go to leaching. And the idea of this is that basically you feed a slurry into a circuit of flotation cells. The slurry is basically a mixture of ground ore with water and chemicals. And afterwards, when it's inside the cell, inside the tank, air is then bubbled through the slurry, which the hydrophobic copper sulfide particles then attach to the rising bubbles and float to the surface, where they form and concentrate as a mineral-laden froth, which then is skimmed off. And to really put into perspective how efficient this process is, well, before froth flotation, copper represents less than 1% of the weight content in the ore. And after the process, after froth flotation, you reach a concentration of about 25% in the weight content of the froth. So it's definitely an interesting process to analyze. And that's the main gist of it. Chris, I hand it off to you if you want to complement a bit of the introduction, or if you want to go straight ahead to the
next slide. Yeah, we'll build on this one. So the copper is concentrated in the froth layer. Next slide, Dennis. And the depth of that froth, determines how much, the quality of that concentrate, and therefore how much copper you're recovering from the system. And so within each cell, the froth is the depth of that froth layer is controlled by the outlet from that cell. However, the hydrostatic pressure in the second cell affects the flow, the inlet flow to that cell. So just by virtue of you have one output going into the second cell, and the water level or the liquid level in that second cell affects the incoming flow. So that is adjacent cells have interact with each other. And so oftentimes in this flotation circuit, where we see four or five cells within the flotation. Here we have a model of 4 cells. And so there's a lot of oscillations that happen just by virtue of the interaction across in controlling the levels in each of these cells. Next slide here, Dennis. And so what we've seen is that if we have a moderately tuned controller, if we tune each of those controllers moderately, we end up with a lot of oscillation, because those individual controllers are fighting each other. And so if you have, in this case, we had a set point change in cell number 2, and you can see there are lots of oscillations that are happening from cells 1, 2, 3, and 4. And then that bottom graph there shows what the output of each of those cells are doing. So there's a lot of oscillations. And so just a set point change in one of those cells causes these oscillations, and causes, it takes about 3 hours for this to settle down to to a stable process. And this is highly upsetting for your for production. And not only just the cells, not only just changing set point itself, we are also by adjusting the airflow in each of those cells, that also causes disturbances to the to the cell control. So that even causes further delays in coming to settling time. And so this is a problem. And so the way that we resolve this, next slide, Dennis. The way that we end up resolving this is by detuning or decoupling the controllers. So rather than having moderately tuned controllers, what we end up doing is staggering that. We take a staggered tuning approach. So the cells, the third and fourth cells, or the fourth cells is we tune it the fastest, the third cell a little bit slower but faster than the second cell, which is faster than the first cell. And so that's how we end up decoupling the controllers across across the circuit. So now when we do have a similar step change in the set point on the second cell by the first graph there, now rather than taking 3 hours to come back to steady state, we're talking more like about half an hour to 45 minutes to for all the cells to come back to steady state. And not only that, when we have changes to the airflow, we end up having, it settles a lot faster. And in the second graph here, we see now that if we have a step change in, a disturbance, in this case, it was the inlet flow into the circuit. Yes, we have a little bit of a response, but again, the settling time is a lot faster than if we had just moderately tuned systems. So this here highlights, highlights the resolution of interaction. Anytime we have interactions across units, regardless of whatever type of process we have, that we would just have to detune those controllers in order to eliminate the interaction with them, because this is a physical phenomenon, and the only way to resolve this is to adopt tuning strategies that eliminates the impact of this physical phenomenon. So this is one of the examples of that we've done in past. So here, all of these graphs that we've shown are part of our case studies that we've modeled, but this is actually because we have customers that we have worked with in detuning these flotation, detuning controllers in the flotation circuits, enough so that we are able to incorporate it into our case studies as a simulation as well. So next slide there, Dennis.
Yeah. And now heading to a brief summary of our webinar. Here, basically, I'm just going to pass through what we have talked, so we can, for anyone who's taking notes, we can, kind of see every single part that we have talked through. So first, we, mentioned a bit of how loop interaction works, that it's physical in origin and most likely is never resolved by single loop tuning alone. Then we went a bit about the economic debate of how much recoverable value you can have. Then we talked a bit about diagnosis, how shared oscillation frequency helps confirm interaction, tools that we can use, such as power spectrum analysis, to really distinguish interaction from other disturbance or noise sources. And then we got to the conclusion that continuous loop monitoring really is the way to go. It converts this reactive intervention into proactive management. And by doing so, integrating monitoring, modeling, and tuning into one workflow really compresses it. And last but not least, here we got to the case study where we talked a bit about decoupling in action, and how correct loop pairing can really deliver the most sustained interaction remediation. So, going through the whole webinar itself and all the points we talked about. And also what is nice to note is that here we have a interaction assessment and resolution checklist, which I believe everybody that is participating in the webinar today will be receiving in their email after the webinar itself. So that's also a nice thing to have, isn't it, Chris?
Oh yeah, this would be quite helpful, and this would have been helpful for me as a process engineer to resolve tuning issues. But we have only a few minutes left here. So Dennis, I'm curious. For Q&A, have you been getting any questions from the audience? Oh, I think. Oh, before we go to the Q&A, we have a final survey question, and here we'd want to, what information would you want to know from, from Control Station? We have tuning software, we have loop performance monitoring software, we have training workshops, we have this PDF on interaction assessment and how to resolve, and we have the OCE calculator. So, what of the things that you've seen or heard of today that are of interest to you, and you'd like to hear or learn more about, select as many as are applicable.
Yeah, and I really want to highlight the OCE calculator again, Chris. So everybody, if you want to, you can also head to controlstation.com and go to the Tools and Calculators tab to go check it out. In my end, all the customers that I have talked to are really impressed by it, and they love to play around with it and to see what types of values it can really help put into perspective the value that is in the table for anybody who's looking for a loop management solution. And I think it's a great way to start as well. Would you say so, Chris?
Oh yeah, again, I'm biased. Process control is my area of expertise, and
Definitely.
Process plants really do struggle a lot with just PID performance, and just by virtue of seeing seeing where they are and seeing what value there is to loop process control improvement, this can really light a fire into help them say, I want to loop performance monitoring because I want to improve my plant and save some money. So yes.
Yeah, and just looking at the number that the OCE calculator gives you, I think it's really is a good motivator for anybody who's looking to adopt a control loop or tuning solution. It's
right,
definitely
and
great.
to convince your managers as well that investing in this is the right thing to do. Yes. All right. So
fantastic. Thank you, gentlemen, for those great remarks and walking us through today's webinar materials. We had a handful of questions submitted during the breadth of the presentation. The question function remains open, so if others have interest in hearing from Chris and Nelson, please feel free to share those thoughts. But let's begin with one that came in very early in the presentation. And Chris, this might be one for you, though Nelson, I'm sure you have a perspective as well. The question is, what types of processes are most subject to loop interaction?
So any process where you have a lot of integration, especially energy into heat integration, this is where you tend to have a lot of interactions, just because the physics of the system is such that the energy content of one loop is affected by the energy content of the other, and so the flows of the individual loops have an issue there. So I would say from my experience, energy systems that are heavily heat integrated are the ones that have a lot of interactions.
Yeah, and to complement you, Chris, the answer I like to give is probably all loops have interaction. It really depends on the severity or the intensity of the interaction. And as you mentioned, energy and heat heavy loops are the ones that really pop out the most.
Okay, Nelson, this next one, I'm going to target you with it. It's a question in two parts, and the first is it practical to compensate for loop interactions by tuning, followed by, is detuning a good solution?
Okay, so that's a great question as well. So as Chris has shown in the case study, tuning can be a good solution as long as we keep in mind the strategy behind it, being decoupling the loop pairings that we have or you have seen in your process. So for example, the staggered tuning approach that Chris mentioned, and Chris, feel free to give more input into this, is a way where you can really decouple and separate each of those loops to achieve a better result. It may be counterintuitive to detune in that scenario, but it really works. And Chris, feel free to add more if you want to.
Absolutely. Yeah, in general, detuning your process is oftentimes a good solution for resolving interaction issues. Just by detuning them, you don't have that one loop fighting the other, and just by virtue of that, you end up with a nicer, steadier operating process. So absolutely.
Great. Chris, this one just came in, so I'm pivoting from the beginning of the session to one that came in. This is from the biotech, the pharma arena. For the mining case study is the question. What were a few of the intermediate analysis steps that led you to select staggered tuning? Is it one of several solutions in the CLPM solution, Plan ESP?
Okay, so what were the steps? It was looking at the power spectrum to see, what were the main frequencies of oscillation, and then using that so identifying the loops. Well, given that they're all in the flotation circuits, and again, interaction is a physical driven thing, so just by virtue of them all being in that flotation circuit, then we know that they're all interacting. But understanding which of those loops is leading versus lagging, this is where we take from power spectrum to cross correlation to then identify, which of those, because we might think that just by virtue of cell number 1 being the first one in the circuit, that might be the interacting loop, that might be leading. However, we can tell what the tuning parameters are set. So once we have this, once we go to cross correlation now, this is where cross correlation helps us identify which of those loops are leading and which is lagging. And oftentimes those leading and lagging is predicated on what tuning parameters you have for the individual loops. So then from there now we can identify that we need to adjust the tuning parameters such that we can stagger the tuning and resolve that those interactions. So the workflow is, power spectrum to identify the loops, cross correlation to identify which one is leading or lagging, and then using that to then determine, okay, how do we want the process to work? And this determining how do we want it helps us to identify which of the loops we want to go, run faster than the other. And so it requires a bit of judgment to determine that last part.
Great. One last question. I know that we're at the end of the session. I'll sneak this in. Nelson, for you, I gather. What could you recommend if tools are available for analyzing loop interactions, but time isn't?
Oh, that's a great question, actually. And honestly, it's a very common issue. It's very, very, very prevalent with a lot of our customers, where they have the tools or they have the necessary equipments to deal with these issues. But if you don't have the time, well, down here in Brazil, Aquarius has a very specialized process engineering team, where we can provide you with services that go through all of these topics that we mentioned today, from diagnosis to action, and to really solve the issues that you have, not only with loop interaction, but with other process control issues as well. So you really don't have to spend that much time looking at it. We can do it for you. And honestly, it doesn't have to be forever. We could be together for the first couple of months or the first year, or for as long as you want to, so we can clear the backlog of offenders, or clear the backlog of issues that you have been facing if you haven't tackled them in the past. And afterwards, maintaining or sustaining performance after this has been cleared is less time intensive. So it's something that the customer, or the client could do by themselves. So if time is an issue, no worries. We can help you with that. We can provide the services and work it out with you.
Great response. Thank you both for your thoughts there with those questions. We have gone well past the designated hour slot. Want to thank everyone for joining us today. If there are questions not addressed, if there are questions that you chose not to raise today in public but would like to contact us, please reach out to a member of the Control Station team. You can use the QR code there to be directed to our website. Additionally, as Chris had noted, next month we'll be pleased to co-host our next webinar with Maxime Lachance of Group BBA. Maxime, former board member of ISA, brings a long history of experience in process control, great perspective, and I'm certain this will be another really valuable session. Thank you very much to everyone today for joining us. Nelson, your remarks and your participation, always great to have you and Aquarius present. And Chris, you're equally well-versed in this, and I'm sure the audience appreciated your experience and perspective. Thanks everyone for joining us. We hope to see you again next month.
All right. Thanks everyone. Have a good day.
Thank you, everybody.